All right, and we're back. So now we're going to talk about buffers. So I don't know how much you know about buffers. Some of you probably know some things about them. Buffers are defined as solutions that resist changes in concentrations. Okay, that's because they are made of a weak conjugate acid base pair. So weak acid, its conjugate base, weak base, its conjugate acid. Okay. They contain relatively high concentrations of both of those so that they can effectively not change pH. So 10 to the negative 3 or more is useful to make that happen. And we try to make their concentrations approximately equal. Now, we can't always do that because of whatever pH we need it to be, but we want them to be close because that gives us the best ability to resist changes in pH. And we'll talk about exactly what that means and how we know that as we move forward. So if that's what a buffer is, then how does that work? Well, if I have a solution that's made with HF and F minus, we'll add some OH minus to that solution. So we start with this HF equals F minus, right? I add some OH minus to that solution. The HF goes down, the F goes up, all right? We can also do it the other direction. We can add H plus, the HF goes up, the F goes down. Okay, but it doesn't change all that much. And because it hasn't changed all that much, that's not going to be that big of a change in our pH. There are a couple of ways that we can make a buffer. So one, I can take like a weak acid, like HF, and add a salt of its conjugate base to it. So NaF, because it contains F minus. So I can mix those two together. Another way that I can do this is to take a weak acid and react it with a strong base to partially neutralize that species. And so when I do that, I have both the acid and the base present when that happens. So that's also going to give me a buffer situation, all right? So we'll see that every time we do a titration, when we get to that titrations, there'll be a region where there's buffering going on, right? So that's a buffer. Now, we say that buffer has a range and a capacity. So the capacity is related to what is the concentration of the acid and the base, because that will determine how much acid or base I can add without changing pH. Okay. The other thing is the range over which that thing works. So the range of pH values over which it works effectively is approximately 1 pH unit, plus or minus 1 pH unit from the pKa of the acid or the pKb of the base. Okay, so that's what we're talking about there. We will talk about the rest of this stuff shortly. Okay, so the capacity, again, is related to the concentrations. So bigger concentrations have more resistance to pH change. And the range is always defined as either the pK, A or B. So I'm just going to leave it as pK, plus or minus 1 pH unit. Okay, so that's what we're talking about for that. Hopefully there are no questions, but that's what we talk about for that. And when we talk about adding a strong acid or a strong base to a buffer, similar to what we talked about for the HF and how that changes, we can add a strong acid or base in that neutralization action. So we can calculate the how much of this we've got, all right? And then once we've calculated how much of each is left, the HA and the A minus, or the BH plus and the B, then we can use an equation called the Henderson-Hasselbalch equation. And I'll show you that equation in just a minute. But we'll do the stoichiometry to figure out how much of the acid that's present has been converted to base, or how much of the base has been converted to acid. Once we know both of those concentrations, then we can do our calculations to see what our pH is. Okay? So we're going to calculate the pH of a buffer. Well, we start with a weak acid. Ka is equal to H plus times A minus over HA. Let's take the negative log of both sides, right? So if I take the negative log of Ka, that gives me pKa. If I take the negative log of H plus, that gives me pH. And if I take the negative log of A minus over HA, it's an expression. I can rearrange a bunch of this stuff, and I can see that pH is equal to pKa plus the log of the A minus, the base, over the HA, the acid. Okay, so you'll hear me say this over and over and over. pH is equal to pKa plus the log of the base of the acid. And that's where this comes from. That is the Henderson-Hasselbalch equation. I will admit, I will probably refer to this as the Hasselhoff equation more than once. It's just something that sticks in my head, so I'm sorry, because I know it's a little confusing for my students, but in my head, they're equivalent. So I apologize if I actually do that while I'm talking. All right. This applies only to buffers. So if it's not a buffer, I cannot use this to calculate pH. Okay? I have to go about it in other ways. Questions about what the Henderson-Hasselbalch equation is? That derivation can be found in your textbook. If you're interested in seeing how it's derived, I'll walk through most of the steps. If you want to see how it's done, you can get that there. Now, can we do calculations with this? Absolutely. We can do what's the pH, POH, H plus, and OH minus of a buffer that is 0.12 molar in lactic acid, which has the formula CH3CHOHCOOH, and 0.1 molar in sodium lactate. Ka for lactic acid is 1.4 times 10 to the minus fourth. Finally, what is the CH3CHOHCOOH concentration in solution? Okay, fine. So the first thing I'm going to do is write down my Henderson-Hasselbalch equation. pH is equal to pKa plus the log, and I just write this as base over acid. And I know they're both concentrations. Since I'm working with an acid that is lactic acid, CH3CHOH, COOH, and the base that I have here is going to be the conjugate base of that, so I'm going to have lost a proton. That's a CH3, CHOH, COO minus. Okay, that's the anion that's going to come from the sodium lactate. Okay, now concentration of the acid. I know that this is 0.12 molar in the acid and 0.10 molar in the sodium lactate, which completely dissociates to give me the lactate ion and the sodium ion. Okay, so now I can put some things in here, right? Because I have a Ka equal to 1.4 times 10 to the minus fourth. So pH is going to be equal to the negative log, the 1.4 times 10 to the minus fourth, that Ka that I was given, plus the log, the concentration of the base, 0.10, over the concentration of the acid, 0.12. Okay, so that's how I get all of those happy numbers there. That means that I'm going to have 3.85, because that's what the negative log of the 1.4 times 10 to the minus fourth is, plus the log, plus, and this log term comes out as negative 0.08. Okay, and that means that my pH is going to be 3.77. Once I have that my pH is equal to 3.77, I know that my H plus is equal to 10 to the negative 3.77. My POH is equal to 14 minus 3.77, and the OH minus is equal to 10 to the negative 14 minus 3.77, whatever that value comes out to be. Okay. And so that's how I get the concentration of my H plus, the POH, the OH minus, all of those happy things. Now, what's the concentration of the CH3CHOHCOOH? Well, I started with 0.12. I've taken out the 1.70 times 10 to the minus fourth. Okay, because that's how much has been converted in this process, because that's my H plus, so I know that that's the case. So since that's my H plus, I know that's how much of the how much of it has come apart. So I do the correction, 0.12 minus that X, that gives me the 0.11983. Sodium lactate is 0.10 molar since it all dissociates and has not reacted with anything. Okay, so that's how I know what that concentration is. Hopefully that's clear, and if it's not, It will be when we get through some more practice. Okay, so that's how we deal with that. We take the Ka, find the pKa, we find the concentration of the acid, concentration of the base, plug everything in, and solve. And once we have a pH, then I can do the calculations that I've been doing, the H plus, the POH, the OH minus, and then find the concentration of the acid, and that's equal to the 0.12 minus the 10 to the negative 3.77, which is my H plus concentration. Okay, so that's what we have for those calculations. Now, let's do another example with the Hasselhoff equation so that you have more to look at and more to think about before we go on. We have oxalic acid, which is C2H2O4. And sodium oxalate, and of course this is 0.234 molar sodium oxalate, which is C2H04 minus. And this is 0.230 molar. The Ka for the acid, 0.056. What is the pH of the buffer? So pH equals pKa plus the log of the base over the acid. And I'm just going to check my exam handouts. I think that the Henderson-Hasselbalch, pH equals pKa plus the log of the base over the acid. So it is included, so you don't need to remember it. I do, but you don't need to. Okay. So we take the negative log of the 0.056. We add this log term of the concentration of the base, which is this one, and this is my acid. So I have the 0.230 over the 0.234. Okay. I do some happy math, and I take the negative log of the 0.056, and that gives me 1.25. I have plus the log of 0.23 divided by 0.234, 9.8 times 10 to the minus 1, so 0.98. I take the log of that answer. It gives me 1.25 plus negative 7.49 times 10 to the minus 3. So I'll add that to the 0.125 because it's a negative number. That gives me 1.24 as my pH. Okay. So what's the pH of the buffer? What are the POH? POH equals 14 minus 1.24. I'll let you calculate that. The H plus is going to equal 10 to the negative 1.24. The OH minus is going to equal 10 to the negative 14 minus 1.24. And then I want the concentration of the C2H2O4, which is going to be equal to 0.234 minus the pH. So 10 to the negative 1.24. And that's how I get all of those happy calculations that I'm looking for. All right? So that's how we do that. I hope that there are no questions about that. You can see that it gets very routine once you've done a bunch of repetition with it. So it's all about knowing what it is. So when we have something that's labeled as an acid, that's the acid. The other thing is the base. We mix those together. We know what their concentrations are because we're typically told. We know what the Ka is for that, so we can use the Ka to find the pKa. It's not that big a deal. This should be fairly easy for you to do. Okay, so I say. But hopefully those are easy points. All right. Now, one of the other things we need to talk about is now I've done calculations with the Henderson-Hasselbalch equation. Yay. I know that a buffer can work in action. It can do stuff. So a buffer is made by adding 0.300 moles of HC2H3O2 and 0.300 moles of NaC2H3O2 to enough water to make 1 liter of solution. Calculate the pH after 0.020 moles of NaOH is added. 5 milliliters of 4 molar NaOH. Okay. So before my reaction, I have the 0.300, and it's in 1 liter of solution. So even though that's the number of moles, that is a molarity because it's 1 liter. So I have a molarity for the CH3COOH. I have a molarity for my OH minus, right? Because they give me 0.020 moles of that. And then I have a number of moles of CH3COO minus, which is 0.300. My change is going to be getting rid of that limiting reagent, so the OH minus. So that's going to go to 0. When it does, that concentration of OH minus is going to decrease the concentration of CH3COOH. And so I take that 0.300 minus the 0.020, and that gives me 0.280. That is then that 0.020 that's gone down from the CH3COOH is then going to go up on my CH3COO minus. So that's where that addition of the 0.020 goes, and that gives me 0.320. Okay, so that is how we look at the number of moles and how they have changed. Now, since this is a 1 liter solution initially, we add 5 mils to that, we can calculate a molarity for our final concentrations to find a pH using the Henderson-Hasselbalch equation. So pH is equal to pKa plus the log of the base over the acid. The volume has gone up from 1 liter to 1.005 liters. So the pH is equal to 4.74 plus the log of the 0.320 moles divided by the 1.005 liters over 0.20 moles over the 1.005 liters, which gives me 4.8. Okay, so remember, we had to do the adjustment in moles and then go back to molarity. That is always required. Our Henderson-Hasselbalch, KAs, all of that is based in molarity, not moles. All right, so make sure that you're working in the right units. After the above solution changes have been made, we then add 5 milliliters of HCl. What's the new pH? So now we're taking the solution that we just had, okay, that we did all those calculations for, and adding some H plus to it. The amount of H plus that I'm adding is the limiting reagent. It's what's going to dictate how much of this is done. So I'm adding H plus, so that means I'm going to take the CH3COO minus, add an H plus to it, and make CH3COOH. So that concentration, the CH3COOH goes up, the CH3COO minus goes down, and we go back to where we were in the beginning because we added the same amount of the same concentration. Okay, so my pH equals pKa plus the log of the base over the acid. That's equal to 4.74 plus the log of the 0.3 moles over 1.10 liter divided by the 0.30 moles divided by the 1.101 liters equals 4.74. And that's interesting because it's exactly the same, which makes sense to me. If the concentration of the base is equal to the concentration of the acid, then that term drops out. It becomes 0. And so the pH is always going to equal to pKa when the base and the acid are equal. Okay, so that is how that works. Right? So sometimes we can save ourselves some work by recognizing that those two concentrations are the same. Questions about that? All right. I have one more example here that we can talk about. That's 0.035 moles of H2C6. H6O6 is mixed, not missed. Wow. With 0.0352 moles of sodium ascorbate, NaCNaH, C6H6O6 in a 2.5 liter vessel. 10 milliliters of 0.25 molar BaOH2 is added. What is the pH, POH, H plus, OH minus, C2H6O, that the acid and the base? Okay. So let's take a look at this. So if I'm going to look at my H2C6H6O6, that's going to come apart to become an H plus HC6H6O6 minus. Okay, initially, that's not a C, that's an R. I have 0.035 moles, and that's in 2.5 liters. And then this one over here is 0.0352 moles in 2.5 liters. And then I do my change to this, right? And I mean, we typically aren't actually using like a rice table per se, okay? And I'm actually not going to do it quite this way. So I'm going to do this in the way that we looked at it previously. So these are going to be moles. This is 0.0350. I'm not talking about that. 0.0352. We do our addition of 10 mils of 0.025 molar BaOH2. And of course, if I have 10 milliliters of 0.25 molar BaOH2, and I know that there are 2 moles of OH minus per 1 mole of BaOH2, then that gives me 10 times 0.25 times 2, and I need to divide by 1,000 to convert to liters. Okay, that gives me 5 times 10 to the minus 3 moles of OH minus that are added to this. Okay, so I've added 0.05 times 10 to the minus 3 moles of OH minus. Now, when I add the OH minus to this, that reacts with the H plus that exists. Okay, so it's going to react with H plus from here, so this is going to go down. And this is going to be 0.0350 minus the 5 times 10 to the minus 3. And this one is going to go up by the same amount. So 0.0350 minus 5 times 10 to the minus 3. And that gives me 0.03. And this one, 0.0352 plus 5 times 10 to the minus 3, is going to be 0.0402. And that's the number of moles again. Now, we can then divide that by the 2.5 liter vessel that we were in. Okay, it was diluted to a 2.5 liter. And then we added 10 mils to it. So 2.5 times 1,000 gives me 2.5 times 10 to the third plus 10 mils, which gives me 2.51 times 10 to the third as a total volume. 2.51 times 10 to the third, 2.51 times 10 to the third. So 0.0300 divide that answer that I had. And that means that this concentration, after we've done this, is 1.1 or 1.195, which gives me 1.20 molar. And this other one, 0.0402 divided by the 2.51 to the third gives me, no, sorry, it's not 1.2, it's 1.2 times 10 to the minus fifth. And this one gives me 1.60 times 10 to the minus fifth. And I know that pH equals pKa plus the log of the base, which is that 1.60 times 10 to the minus fifth, over the acid, 1.20 times 10 to the minus fifth. Okay, and my pKa is going to be given, where is my Ka? Do I have a Ka? Hopefully I have a Ka. I did not get Ka, so hopefully it's in this table. So ascorbic acid has a Ka of 8.0 times 10 to the minus fifth. So pKa is going to be equal to the negative log of 8.0 times 10 to the negative fifth, which gives me 4.0. No, 4.10, because it's going to round up. 4.10. So 4.10 plus, and then we have the 1.6 times 10 to the minus fifth. We divide that by 1.2 times 10 to the minus fifth. And then I take the log of that term, and it gives me 0.124. I add that to the 4.10, and that gives me total, and actually this was 0.124. And so my pH is equal to 4.22 after that process happens. Now, if I'm then going to add 10 milliliters of acid to that, we're going to do the exact reverse. And so what's going to happen when we do that is that the pH is going to be equal to the pKa plus the log of 0.350 over, and rather than 2.51, it's going to be 2.52 times 10 to the minus third. 2.52 times 10 to the minus third divided by 0.0352 times 2.52 times 10 to the minus third. Because once we do that adjustment, those pHs are going to go back to exactly what they were in the beginning, since we've countered the change that we made initially. So if I do that, and my pKa, if I remember, 4.10. 0.0350 divide 2.52 is 10 to the third. This gives me 1.39 times 10 to the first. Oh, wait, hold on, sorry. That's not negative 3. It's positive 3. So 10 to the third, 10 to the third. So 0.0350 divide 2.5 to the third, 1.4 times 10 to the minus fifth, 0.0352 divided by 2.52 to the third equals 1.4 times 10 to the minus fifth, which means that the pH is equal to the pKa, which is 4.10. okay? Which is exactly what I was expecting. It's what we had before, so that's what we would expect again, okay? So that's using the Henderson-Hasselbalch equation. Is it a lot of pieces to put together? Yeah, it can be. It can be. But that is how that works. So hopefully there are no questions about that. Now I have some sample questions here. These are samples for everything that we've talked about here. So I'll put these answers on D2L. Sample questions on D2L. And I will let you ask me about them if you have specific questions. If I have time, I'll record an answer or a thing like this for it. But now I want to get ready to talk about experiment 2. I'm going to go ahead and stop this so that we can talk about experiment 2 in just a few minutes. All right. I'll talk to you guys later.